Hey everybody, I wanted to do a couple more examples of the spring type of problems for work. And so I have a couple and then I'll move on to the lifting fluids problems in another video. So this example, if 60 newtons of force is required to keep a spring compressed 10 centimeters, how much work is done during this compression? And the second part of this question, how much work is required to compress the spring to a length of 25 centimeters if the natural length of the spring is 40 centimeters? So we can use the 40 for both parts because that is the same spring. So going back to the notes that we talked about in class, so I know that the force by Hooke's law, the force is proportional to the displacement from equilibrium. So we can say F equals kx for a spring. And so this is force. And the work, then, because this is a variable force, if you have a spring, and as we talked about, if you stretch it, so if this is your equilibrium point, and then as you stretch it past the equilibrium point, to find the work, you have to kind of like take little chunks of the spring and find what is the force there. So the force is changing as you go through. So that's why for work we need an integral. So work will be the integral from the equilibrium point, so from 0 to however far you stretch it, to A of force times displacement. So our force is kx and the displacement is dx, right? If I'm finding it for each of these little things, that's a delta x, delta x, delta x. As we put them into our Riemann sum and we take the limit as n goes to infinity, that becomes dx. So this is the work. And just for sometimes we may not necessarily always be doing things from equilibrium, so I'm just going to say from A to B. So that will be the work. So the force is just kx and the work is an integral. So let's see. So what are we given here? We're given 16 newtons of force is required to keep a string compressed 10 centimeters. So we want to know how much work is done. So we need to first find the constant of proportionality. Now notice that we're given newtons here. And remember newtons, that means that we have meters in our units. And here we're given centimeters. So I need to be able to convert that to centimeters. So 10 centimeters is 0.1 meter. So make sure that our units match up. So what I'm going to have is I have 60 newtons of force. So F is 60 is equal to K. We don't know what K is. And X is the distance from equilibrium. So I'm compressing it 10 centimeters, which is 0.1 meters. So I'm going to do 0.1, which means solve for K. So we get that K is 600. Remember, this is newtons and this is 0.1 meters. So the units for our K end up being newtons per meter. And now that I have K, we can go back and put in the work equation. So work is going to be the integral of kx dx. I already know K. So K is 600 and then x dx. And we're going from where to where? We're compressing it 10 centimeters from equilibrium. So we're going to go 0 to 0.1. And you may be wondering, why aren't I using negatives, right? If I have my spring is 40 and I'm compressing it, that means we're going this way, 10 centimeters, 0.1 meters. Why don't I say negative? You could. Then that would make this x negative, which then when you plug in the negative, they'll cancel out anyway. So then we can just treat it as the distance instead. Instead of going distance to the right, we're going distance to the left, but you can keep it as just the distance as a positive number. And so now we integrate this. So I'm going to have integrate 600x. So that will mean x squared divided by 2, so 300x squared from 0 to 0.1. And plug in 0.1, so I get 300.1 squared minus, when you plug in 0, you get 0. And what does this become? This is 300 times 0.01, which ends up being 3. And what are our units? Will be joules. So our K here is newtons per meter. So this is newtons per meter. You have meters times meters. So you end up with this meters cancel. So you end up with Newton meters, which is a joule, which is a unit of work. So that will be the amount of work to compress 10 centimeters of our spring. Now, how much work is required to compress the spring to a length of 25 centimeters from 40? So now notice that this is given us a specific length when the spring reaches 25 centimeters, not compressing at 25 centimeters. So we have to pay attention to the wording. So for that part, we want, we have our, so I'm gonna, even though I don't have part B, I'm gonna call it B. So compressing to 25 centimeters. So let's picture our spring. So the natural length is 40 centimeters. And if we compress it to a length of 25 centimeters, so you're compressing it so that it measures 25 centimeters now, how much did we compress? So that will be that distance. So it will be 40 minus 25, which is 15 centimeters, and we can change it to meters. So 15 centimeters is 0.15 meters. This is the same spring, so our constant is the same. So K is still 600. So F is still 600x. So for compressing it this much, we're going to do, so the work is the integral from 0 to 0.15 of our force times displacement. So 600x dx. And we already integrated that. It's still 300x squared. And we put in 0 to 0.15 and plug in the 15 centimeters. So you have 300 times 0.15 squared minus, plug in 0, you get 0 again. And when you do this on a calculator, I got 6.75 joules. And so what is the difference here between the two parts? This one said the spring was compressed 10 centimeters, right? That was part A, so we went from 0 to 0.1. But part B says how much work is required to compress the spring to a length of 25 centimeters. So that means when the spring measures 25 centimeters, not when you compress the 25 centimeters. So these problems is, reading the problem, it makes a huge difference in how you set it up. So my second example is, what if you're given work? So let's read it. I'll let you read it and then we'll start it. Okay, so in this case, we are given the work required to stretch a spring from 10 centimeters to 12 centimeters, and another 10 joules is needed to stretch it from 12 centimeters to 14. What is the natural length of the spring? So we don't know the natural length in this case, but we're given work. So remember, force is, for a spring, is Kx, and the work in stretching or compressing the spring is the integral from A to B of the force times the displacement, so Kx dx. So in this case, we're given work, so we have to pay attention to that. 6 joules of work, 10 joules of work. So we're given work, not force. So because I'm given work, I'm going to be using this formula. So that means that 6, the work, is equal to the integral from where to where of Kx dx. Right, I don't have K in this case. So, and what are my limits of integration? So just look at the spring. So if I have my spring, we don't know the length, so let's call it L. And so that will be my x equals 0. And then we stretch it from 10 centimeters to 12 centimeters. So we stretch it 10 centimeters past is natural length, so that will be 0.1. And then to, not drawn to scale here, 0.12. So we're looking at the work that we're given is for this stretch, the blue highlighted part. So what are going to be my limits of integration? Well, it's not, because we want to know the natural length of the spring, I'm not necessarily going to use 0 for it because I want to know what L is. So that means that it was stretched this much. So we're going to say, what's this distance? Well, it's 0.1 minus L. So that's going to be my bottom limit, 0.1 minus L, and my top limit is this distance, so 0.12 minus L. And we can integrate this. And so when we integrate it, I'm going to have, what do we have? 6 is equal to the integral, so kx squared over 2 from 0.1 L, 0.1 minus L, and 0.12 minus L, and plug it in. So I have 6 equals k over 2 times 0.12 minus L squared minus 0.1 minus L squared. And so this is kind of hard, right? Because we have two unknowns. I don't know K and I don't know L. So you might be thinking, how do we solve for K and L? Well, I've only used part of the problem given to me. 6 joules of work is required to stretch a spring from 10 centimeters to 12 centimeters. And another 10 joules, so there's another work there to stretch it from 12 centimeters to 14 centimeters. So I can set up another integral then. And that second integral is going to be for the work of 10 joules. So 10 joules of work is needed to stretch it from 12 centimeters to 14 centimeters, right? So that will be 0.12 minus L to 0.14 minus L if we draw the same kind of picture of kx dx. And integrating in the same way, I'm going to have 10 is equal to k over 2 x squared from 0.12 minus L and 0.14 minus L. So essentially notice what we have. You're going to have this equation, and once you plug in the 0.14 minus L and 0.12 minus L, we're going to get a second equation. So 10 equals k over 2 times top limit first, so 0.14 minus L squared minus 0.12 minus L squared. And so now I have two equations and two unknowns, so we create a system of equations and solve. So let me write down what our system will be. So I have a system of equations. So the first equation is 6 equals to k over 2. So we're going to multiply both sides by 2 in a minute. And I have, what, 0.12 minus L squared minus 0.1 minus L squared. So that's one equation. The other one is 10 equals k over 2 times 0.12 minus L, 0.14 minus L. Minus 0.12 minus L squared. So we can do some algebra here, right? So change our equations. 12 equals k, and we can multiply all these out. And this one would be 20 equals k times 0.12, 0.14 minus L squared minus 0.12 minus L quantity squared. And so now I have a system of equations, two equations, two unknowns. So we can either solve by substitution, or you can solve by elimination and solve for k. And really we're after L. L is the natural length of the spring. So from here I would want to solve somehow either substitution or the elimination method or for a system of equations to find the value of L. I'm going to let you go through that algebra on your own, and like I said, you can either use the substitution method or the elimination method, but once you are done with the algebra here, what you'll find is that K, you're going to get 10,000 for K, and the length of the spring is 8 centimeters. So you're going to get it in terms of meters here, but you can convert it back to centimeters. So the length of the spring is the natural length is 8 centimeters, and you'll be done. So I just wanted to illustrate a couple of more examples of what the difference is when you're given something to solve for the force and how you find your K just by plugging in force equals Kx. And when you're given the work instead of the force. And then, so when you're given the force, you just plug it into the F equals Kx to get your K. But when you're given the work, you have to plug in 6 into the integral. The integral from A to B of Kx dx. So pay attention, what are you given? Are you given the force or are you given the work? Because that's going to dictate which equation you use. Okay, and I'll do another video for lifting fluids problems.